Assalamualaikum and hello again everyone. We've come to part 3 of the probability topic where we will learn how to find the probability of an event. In an experiment, the probability of an event is the likelihood of that event occurring. Probability is a value between and including 0 and 1. If PA represents the probability of an event A, then PA equals to 0 if and only if A is an impossible event. PA equals to 1 if and only if A is a certain event. The sum of the probabilities is equals to 1. Given the two events, A and B, PA is larger than PB if and only if event A is more likely to occur than the event B. Furthermore, if A1, A2, A3 is a sequence of mutually exclusive events, then the union of all the events is equals to the sum of the events. Here is an example of a coin tossed twice. What is the probability that at least one head occurs? Here is the sample space. If the coin is balanced, each of these outcomes would be equally likely to occur. Let A denotes the event of at least one head occurring. Then, PA equals to 1 over 4 plus 1 over 4 plus 1 over 4, which is equals to 3 over 4. Next, a dice is tossed in such a way that an even number is twice as likely to occur as an odd number. If E is the event that a number less than 4 occurs on a single toss, find PE. Here is the sample space from 1 to 6, and then we assign a probability of W to each odd number and a probability of 2W to each even number. Since the sum of the probability must be 1, we have 9W equals to 1 or W equals to 1 over 9. Hence, probabilities of 1 over 9 and 2 over 9 are assigned to each odd and even number respectively. Therefore, we have PE equals to 1 over 9 plus 2 over 9 plus 1 over 9 equals to 4 over 9. Next, we consider the previous example. Let A be the event that an even number turns up, and let B be the event that a number divisible by 3 occurs. Then find PA union with B and PA intersection with B. So here is the subset of event A, consists of 2, 4 and 6, and B with the element of 3 and 6. By assigning a probability of 1 over 9 to each odd number and 2 over 9 to each even number, we have the event for A intersection with B, a total of 2 over 9. And then the event of P in A union with B is a total of 7 over 9. Now, let's say rule 2.3, where PA is equal to small n represent the number of outcomes in the sample space n divided by all the outcomes of an experiment is called the sample space with capital N. In this example, a statistics of 25 vans, 10 lorries, 10 cars, and 8 motorcycles were caught in the traffic jam. If a vehicle is randomly selected, find the probability that the vehicle chosen is a van and a motorcycle or a car. Since 25 of the 53 vehicles are vans, the probability of the event V selecting a van at random is PV equals to 25 over 53. Since 18 of the 53 vehicles are motorcycle or a car, it follows that P event motorcycle union with car is 18 over 53. Based on theorem 2.7, the probability to get an event A or event B can be written as the probability of A and union with B. This is equals to the probability of event A occurring plus the probability of event B occurring minus the probability of event A and event B occurring together. Consider the Venn diagram here. The PA union with B is the sum of the probabilities of the sample points in A union with B. Now, PA plus PB is the sum of all the probabilities in A plus the sum of all the probabilities in B. Therefore, we have added the probabilities in A intersection of B twice. Since these probabilities add up to PA intersection with B, we must subtract this probability once to obtain the sum of the probabilities in A union with B. Now we can deduce corollary 2.1. In mathematics, a corollary is a theorem connected by a short proof to an existing theorem. Sometimes you may be dealing with two events that are mutually exclusive. For mutually exclusive event, the probability of get an event A and B together is 0. Therefore, the probability of getting A or B becomes PA plus P of B if A and B are mutually exclusive event. But you can always use the formula in theorem 2.7, which will always work regardless of what type of events you're dealing with. Corollary 2.2 suggests the probability that at least one occurs is the sum of the probabilities of occurrence of the individual events. The third corollary simply states that the highest value of a probability or unity is assigned to the entire sample space, which is equals to 1. Theorem 2.7 and its three corollaries should help you to gain more insight into probability and its interpretation. The inclusion-exclusion rule can be generalized to unions of arbitrary number of events. For example, for 3 events A, B, and C, the rule is stated here in Theorem 2.8. Example 2.29. Please take some time to read and understand the problem here. So, PA is equal to 0.8 and PB equals to 0.6. Then, the probability getting offers from both company is PA intersection with PB. Is equals to 0.5. Therefore, applying the additive rule, you will get 0.9 or 90% chances of getting at least one offer from these two companies. Next, what is the probability of getting a total of 7 or 11 when a pair of fair dice are tossed? Let A be the event that 7 occurs and B the event that 11 comes up. Now, a total of 7 occurs. We have 6 samples out of 36 sample points. Then, B, a total of 11 occurs for only 2 of the sample point. PA equals to 6 over 36. Then PB equals to 2 over 36. From the event element, we can see that A and B are mutually exclusive. So, according to corollary 2.1, PA union with B equal to PA plus PB. The sample space of the total outcome is 36, so the probability of getting 7 or 11 is 2 over 9. This is another example of mutually exclusive event where we can apply corollary 2.1 on how to find the probability of a given buyer to purchase a new automobile in one of these colors. So, let event G for green, W for white, R for red, and B for blue. Then, the union of all events equals to the sum of the events. For every event defined on S, we can define a counterpart event called its complement in theorem 2.9. The complement A prime of an event A consists of all outcomes that are in S but are not in A. The keyword in the definition of a complement is not. Since we also know from the definition of A prime that it includes all the events in the sample space S that are not in A, so PA plus PA prime equals to 1. Example 2.32. What is the probability that the mechanics will service the least 5 cars? Let A be the event that at least 5 cars are serviced, and A prime is the event that less than 5 cars are serviced. Here are the sample space for A and A prime. To simplify solution of some probability problems, if PA prime is easier to calculate in this case, then PA is equal to 1 minus the complementary elements. This is the final example of the topic today. Please take some time to understand the given problem. The example is about the engine cable specification. There are conditions for the cable that are likely to meet the specification and the defective condition. As for the defective condition, there are two lengths of cable where some are larger than 2010 millimeters and some are smaller than 1990 millimeters, and these two events is equal. So the probability that the production procedure meets specification is equals to 0.99. And the question asks you to find the probability that a cable selected randomly too large and the probability that a randomly selected cable is larger than 1990 millimeters. So to start solving the questions, we let M be the event that cable meets specification. So PM equals to 0.99. It is given in the questions. Next, we let S and L be the event that cable is too small and too large. So S for small, L for large. So these two events are equal, so we can say that PS equals to PL. Then 1 minus 0.99 over 2 equals to 0.005. Denoting by X the length of a randomly selected cable, we have a range of P, which is from 1990 to 2010. This is the cables that meets the specification, which is PM equals to 0.99. So for the question asked to find a randomly selected cable is too large is in this range, which is PX is larger than 2010, and this is equals to PL equals to 0.05 that we have computed previously. And then the second one is to find the probability where the cable is larger than 1990 millimeters, which is in this range. Okay, so PX is larger than 1990 is equals to PM here plus PL. Then we've got an answer of 0.995. So this problem can also be solved by using theorem 2.9. Why don't you give it a try and see if you can find the same answer as what we did here. Before I end my video today, I leave you with some of these questions. I hope you enjoyed the video and thank you for watching.